All right, this is going to be part 2 for the XFOIL assignment. And during this video, we're going to be comparing the different Reynolds numbers to the Clark Y airfoil. And ahead of time, I have completed these calculations and these things. I'm just going to go through this kind of as a step-by-step to show you that I actually did them. So first, I'm going to show you that I have my file uploaded here. Where is it at? Let me click that. Go to XFOIL. Again, this is our Clark Y data that we got from the UIUC site. These top set of XY coordinates need to be inverted and then put into 7 decimal places in this specific order in order to get your results to converge properly. So I'm going to minimize that. We're going to minimize that. And so first, let's do the inviscid flow. So we're going to do load Clark Y.dat. We'll load that up. We can type in, what was it, a pane, get our 160 there. So next we're going to go to opper. We're going to change it. Well, actually, because it's an I, that means it's inviscid flow, so we can leave it the way it is. So now what we're going to do is we're just going to go to, typically you would do PACC, similar to last video, and it would allow you to record your data into a file that you could then convert to Word and then analyze your results. Again, I already did that, and I will show you the results in a second, but for time's sake, I'm just going to quickly show you going from -5 to 15 in 1 degree increments. And here we go. These are our values here. And these values will match up with what I have in the document. So let me minimize that really quickly. Go to XFOIL data, part 2 data. Okay, so for inviscid flow, we're not going to have a drag coefficient at all, just because there's no need to. Actually, first, let me show you the actual file itself. Let me exit out of that. Go to here. I'm going to show you the actual file that I opened up. So, open this in Word. So this is the actual file that that was saved onto my computer, which is the same file you see. If this thing would be nice to get out of my way. Hold on, give me 1 second here. The data you see, wow, there's a lot of tabs open here. The data you see here matches up with what is on here when you see number to number. So again, just proving that this was done on this computer. So let me minimize that. We'll click exit on that. Is part 2 data open already? I believe it is. Okay, so for the laminar flow, these are our results here. And for our turbulent flow, these are results here. And I'll actually quickly show you how I got those results. So we'll go back into XFOIL, we'll go to load, we'll load our data, do pane, and we'll go to opper, change it to viscous, and we'll do 300,000 Reynolds number. Is that 300,000? It is, okay. Again, if you're going to make a new file, PACC, again, that's already been done. So we're going to just show the results. We'll do SCQ, -5, 15, 1, and our results converge again. We'll exit out of that, and we'll click quit. I quit it just so I can refresh everything. And for our last turbulent case, we're just going to upload clark.dat. Pane, change the nodes correctly, opper, viscous, 3 million, PACC if you're saving your file, seek -5, 15, 1, and there we go right there. And that is our data. And again, I'll quickly show you the Excel and the graphs I did. So here we have our angle of attack versus our lift coefficient, and we actually do have a little bit of some outliers here. I'm actually going to change this chart design really quick so we can see that a little bit easier. As you can see here, we have a little bit of an outlier with our laminar flow, but once it gets to a certain point, I believe -4 degrees, then it starts to even out again. Over here, the outlier isn't as prevalent in the drag coefficient one, but again, when we see this angle of attack versus CL over CD, we see that outlier again, and that may just be due to convergence issues, even though it did converge. Let me quickly change the chart type so we can see that a little better. So you see the general trend. Once it hits -4, it kind of just, it flattens out and looks a little bit similar to the turbulent flow, but I don't know why this 1 point is just always out of place, no matter how many times we've done this. But again, we get the general flow and the idea behind it, and we can see the trends. And that's honestly all that matters. Let me change this type as well. So we see a little bump there. Yeah. So it's a little bit off, but it's the general trend can be found through this data, and that's really the purpose of this. So I believe that was all that was for this part. The other thing to note is that you can find your maximum CL over CD values by basically just typing, you can do equals MAX, and then you can highlight your column and click enter. And again, we get the same value there. So I'll just click exit on that. And the maximum for turbulent occurs at 5 degrees. I actually have the data tabulated in my Word document, so I'll go there really quickly. Up here. So our maximum lift coefficient for inviscid flow is 2.189 at 15 degrees. 300,000 is 1.3707, and for 3 million it's 1.6959. For the maximum drag coefficient, because inviscid flow doesn't have drag, you wouldn't have any drag, so it wouldn't be applicable. So we have 300,000 and 3 million, the values are here. And then for our last one, when you're comparing the CL over CD, you wouldn't have an inviscid ratio as well, because you wouldn't be able to divide by 0. So you would have an infinite number, which wouldn't be applied to here. And again, here are the graphs below labeled with the figures. So that concludes part 2 of assignment 1, and stay tuned for part 3.